let's now let's now work with expected value with some concrete examples, hoping to illustrate both the computations involved to find expected value of a random variable, but also to illustrate what it could mean in context of these real-world examples. So, to jog your memory, we're working with, again here, the random variable that represents the sum of two dice faces when we roll two balanced six-sided die. So I have in front of me already written the probability distribution table for this random variable, the first column being the support values, all the possible sums that we can get, along with their probabilities, which we calculated directly in a previous video, but now I've represented them as decimal numbers, just for the sake of illustration, with both working with decimal numbers and fractions. So what is the expected value? First, let's anticipate what this expected value means. So remember that we said expected value, you can think of it as the mean of all outcomes when you repeat this experiment infinitely many times. So imagine a gambler who sits there for all of eternity, from now until the end of time, and plays this game over and over and over again, each time getting a different sum. And at the end of eternity, they take their sums and they calculate the mean, the population mean. So in context here, what we're saying is this is the average value we expect to obtain. So in the long run, when we take the mean of all our values, we expect to get this value. Now, we've seen this distribution graph before, so we know that it's symmetric. We know that the graph looks something like a triangular set of vertical bars where the peak happens at 7. So 7 is the most likely outcome among the set of all the outcomes here. So we expect that it'll be, if not exactly 7, near 7. Let's see if that bears out. So to calculate it directly, remember that we need to sum over all the possible outcomes the outcomes themselves multiplied by their probabilities, so by their likelihoods. And this will give us the expected value. Specifically here, we're looking at the sum from x equals 2 to 12 of x times p of x. So we will have between 2 through 12 terms. So if you count those up, there should be, I think that'd be, 1, 2, 3, 11 terms, 10 terms. And when we do that, we're going to take, in each row, take 2 and multiply that by its corresponding probability, add that to 3 times its corresponding probability, and so on. So 2 times 0.0278 plus 3 times 0.0556, and so on down the line. I won't bore you with the details, but you can fill them in yourself. And we're working with approximations of these values. If we had been working with the fractions, while we would have to do some arithmetic with fractions, which I know is not everyone's cup of tea, you could still get a more precise answer than what we are obtaining, because we actually end up getting that this is 7.0007. And if we had calculated this directly, we would get that mu is exactly equal to 7. So that's how we would carry out this calculation. And it takes the same format every time. Now let's see another example where we understand the implications of expected value to mean how insurance companies remain profitable. So this is a very simplistic example. It is not meant to be representative of the full breadth of what the health insurance industry does or how it profits, but for a very simplistic example of this effect, let's imagine that you, I'm going to draw a stick figure representing you, have health insurance. So you have health insurance with health insurance company, no names for legal reasons. And the premise of having health insurance is you pay premiums, so every month you pay them a premium that is your contribution to your health insurance plan. So let's just say you pay $1,000 a month. If you are an independent contractor, or if you are self-employed, then this is not far off from reality. Now, normally, you use health insurance for for regular checkups, but really the benefit is you are hoping that in the event that you get seriously injured, for instance, getting hospitalized, which is a very rare event, but it'll be hopefully covered by your health insurance, so you won't have to pay out of pocket. So the idea is you can think of it as a very simple experiment where either at some point in throughout the year you get hospitalized or you do not. If you do get hospitalized, which has a probability, and for the sake of simplicity, we're using very simple numbers, a 1 out of 23,000 chance of occurring, or in other words, 22,999 times out of 23,000, you don't get hospitalized that year. However, this is what's going to happen if you do get hospitalized. If you do get hospitalized, then the health insurance company, HIC, pays out $20,000 in benefits. Obviously not to you. That would be going to the hospital or the healthcare provider that is specifically taking care of you. But that means you don't pay that out of pocket. Now, if you don't get hospitalized, you get nothing, right? There's no benefit that happens there. You have the good fortune of not getting hospitalized. So what we can do then is let's think of this random variable, which is the profit that the insurance company makes every year from you. So for those of you who need the refresher, remember that profit is the revenue, minus the costs associated with their transactions with you. And we can organize this information using a modified distribution table. So we have two outcomes again. I'm taking now our probability tree diagram and I'm representing it here. So either you get hospitalized or you don't. Now what's their profit? So what's the value of X? If you're hospitalized, now you've paid $1,000 every month. So the revenue, regardless of what happens, is always going to be $12,000 from you every year. And the cost might either be the $20,000 or it could be nothing. So their profit ends up being either negative $8,000 or $12,000. But the probability of each outcome, so the probability of X, that's going to be the same probabilities that we wrote earlier, which is 1 out of 23,000 and 22,999 out of 23,000. So now what we have is, if we think about the expected value here is what in the long run HIC's profit from you. So the average out over however long you happen to have their health insurance plan. And now we can directly calculate this. So we have all the pieces we need, which is we have the two outcomes. So the outcome in which you're hospitalized times that probability plus the profit when you're not hospitalized times the probability of not being hospitalized. And if we calculate that, now this time we're working with fractions, so, follow your nose. And this is approximately 11,999 and 13 cents. Does this make sense? So we're accounting for just one possible outcome relating to your health outcomes. But in the aggregate, averaged out, every year, your health insurance company is getting this amount of money from you. And this loss of approximately 87 cents is what is being accounted for in the probability that you are in fact hospitalized that year. So it would be better for the health insurance company for you to have a very low probability of being hospitalized versus not being hospitalized. And this is true for all sorts of other variables that they consider in taking you on as a customer. If you're interested in this branch of business, you may be interested in checking out actuarial science and the science of risk, and specifically risk management. This is obviously from the perspective of the health insurance company, so take it with a grain of salt. But these sorts of calculations and much more complicated ones are literally what health insurance companies do on the day-to-day.